Good morning, class. This is our second video. The topic of these notes is called set builder notation and interval notation. Okay, this is for Math 111. Today's date is the 18th. Our question that was going to guide us for today is, how do we write the domain? So there's several ways to write the domain in several different notation, and we're going to cover that today. Again, as I do these notes, you can pause whenever you need to catch up. And if you have any questions, try to get those questions to me via email or through the remind message. We're going to have 4 examples here that are very detailed of finding the domain. So the first example is f of x equals x squared plus 5x. Now we know a lot about these kind of functions because we see them a lot. We call these types of function where it's just a straightforward x squared plus 5x plus a term plus another term, right? These are called polynomial functions. Polynomial functions. And what's special about polynomial functions is that its domain is always all real numbers. Domain is all real numbers. Right? That's always going to be true about polynomial functions. And so what I'm going to do is I'm going to highlight that polynomial function always have all real numbers for its domain. Okay? So now, taking that, how do I write this as a domain, right? And different notation. Because this right here is already good enough. That explains you the domain. But there's going to be problems where it's going to ask you for the domain in a certain notation. And so every time you see me do a little line here, it's because there's 2 ways of doing a domain, okay? And so I'm going to teach you 2 ways, set builder notation and interval notation. So this right here is going to be the set builder notation. And this one over here is going to be the interval notation, okay? So when you do set builder notation, we have to have the curly brackets because we use the curly brackets for the set. And we say for what variable x, such that what? Such that this x has all real numbers. And there's a certain way of reading this. I'm gonna read it to us. Well, I'm gonna write it to us. So we say the curly bracket x, the little line here, x, this little e symbol here, and then the r with the little 2 dashes here, and then the close it with the curly brackets again. So when we read this is how we read it. The set of all x such that x is all real numbers. Right? And put in quotations so that we know. The set of all x such that x is all real numbers. The set of all x such that x is all real numbers. Okay, that's how we read it. What about interval notation? Interval notation is very nice and very straightforward. It has symbols that we've all have seen. This is very kind of new to us, right? And so for interval notation, we just use the interval. The domain is from the interval. Well, for all real numbers, right? If it's all real numbers, then what symbol do we use for all numbers? We say infinity, right? For all numbers. But we want to say all the negative numbers, and we use parentheses, and all the positive numbers. So infinity. So negative infinity to infinity. That's how we read it. the domain of this relationship or the function is from negative infinity to infinity, and that's how we read it. And it's an open parentheses and a closed parentheses because we never reach infinity or negative infinity. So it's always the open means it's open, like an open circle, and a closed circle. Closed circle means it's a bracket, and so we'll get to that very soon. Okay. So that's the first example. Let's go on to the second example. F of x equals 3x over x squared minus 4. This function is different because it's not a polynomial more. The top is polynomial, the bottom is a polynomial, but together is not a polynomial. This is a function that has a quotient. So function with a quotient. Okay, so it's something over something, right? It's something over something. And so when we have these situations here, we have seen this before. We know that this denominator cannot be what, right? We know that this denominator cannot be 0. So we're going to say x squared minus 4 cannot equal 0. And we need to find that place where the x will give us 0, because that's where it does not exist, right? And so what we need to do is we got to figure out where is this x that gives us 0. Okay? So we solve for it. So we only look at the denominator. We solve for it. We do some algebra. We plus 4 both sides. We need to get rid of the square, so we square root both sides. But we know this about algebra and doing square root to both sides. When we do that, do not forget the plus and minus. That's very important when we do the square root to both sides. So then we have x equals, well, what's the square root of 4? It's going to be 2. So we have negative 2, and we also have positive 2. So we have this. What does this mean? It means that we have two places where the denominator is going to be 0, negative 2 and 2. And remember that if we graph this or we think about it, that these places will give us places where the function does not exist. This means that there's asymptotes here, right? Asymptotes. So just to remind us that there's asymptotes at these locations of 2 and negative 2. That's why we don't want to have 0 in the denominator. And so how do we write this in as a domain, right? In set notation and interval notation. So, and I want to highlight this. Functions with quotient, we always want to look at the denominator so that, look at the denominator where it does not equal 0, okay? So I'm gonna draw, let me draw a line over here so that I don't need to go down here. So set builder notation. I think I drew my little line too far down. So it's all real numbers except these places. So how do I denote that? So all I want to say is x does not equal negative 2. And I ran out of space here. That's not good. Should have did it. And then comma. And then x does not equal positive 2. And then we close it. Okay. And I want to continue on the right, but I drew my little line over here already. And I shouldn't have done that. So that kind of limited my space there. Okay. So let me move this to the left because I'm not liking it. It's bugging me. So x, the set of all x such that x does not equal negative 2, comma, x does not equal 2. And then we close it with the curly bracket. Okay. So that's set notation. For the other notation, we got to do this in parts because it's everything except these places. And so we got to do it in parts. So we got to say it's from negative infinity all the way up to negative 2, right? We stop at negative 2. And notice that it's open. We don't include those. It's also from between negative 2 and 2, right? So we want to say also from negative 2 to 2. And then lastly, it's from 2 to infinity. from 2 to infinity. So for this one, we got to write it in parts because these places are telling us where we stop and we will continue. Stop and then we continue. So we start from negative infinity all the way up to negative 2, between negative 2 and 2, and then from 2 to infinity. That's example number 2. Let's go on to example 3. For example 3, g of x equals the square root of 4 minus 3x. Notice that this function is different, right? We call these radical functions, or functions with radicals. So you can flip that around. And we know this about radicals, right? We know this about radicals, that we cannot have negative numbers under their square root, right? And so let's write that. Cannot have